Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to be taking a look at Chapter 6, Section 2, which is going to cover the different types of standard enthalpy changes. So this is going to be a very definition heavy chapter section, and we're going to look at essentially the vocabulary that we use in enthalpy change conversations. So let's start with the word standard. The word standard in chemistry means something very specific. Whenever we compare enthalpy changes, which to recap we said were the energy changes, specifically the heat energy changes that come along with different chemical and physical processes. In order to compare them properly, we need to compare them at the same conditions. So we use what we call standard conditions. That's why at the beginning, this section is called the standard enthalpy changes, meaning that all of these are going to happen at standard conditions. Now, what are standard conditions? Well, standard conditions are just conditions that chemists and scientists have agreed are going to be the conditions we normally work at. The most standard, the most commonly used conditions for temperature, pressure, and a few other things. Now, for standard conditions, whenever we talk about the standard enthalpy change of something, that standard should tell you that this is happening at these conditions. Those conditions being a pressure of 101 kilopascals or 101,000 pascals to make the conversion, a temperature 298 Kelvin or 25 degrees Celsius to make the conversion, and that each substance involved in the reaction is in normal physical state at room temperature and pressure. Meaning that if we're working with water, that water is liquid because the water is liquid at room temperature and pressure. If we're working with diamond, the diamond is solid because that's how it's normally found. If we're working with mercury, the mercury is liquid, so on and so forth. So those are the three conditions when it comes to enthalpy changes, because as we have different conversations throughout the curriculum, some of these might be added on, some conditions might be added on to these. But the standard conditions when it comes to enthalpy changes are the following: just 101 kilopascals of pressure, 288 Kelvin, and each substance is at its normal physical state for room temperature and pressure. Now, the symbol that we use in order to show that an enthalpy change is standard is this right here. It's a circle with a line going through them. Anytime you see that symbol, it indicates that the enthalpy change is standard, meaning that it was carried out at these conditions and therefore can be usually compared to most of the enthalpy changes we see. So, for example, if we had the enthalpy change of the combustion reaction between methane and oxygen to get carbon dioxide and water, this reaction can be carried out at 298 Kelvin, which is 25 degrees Celsius. It could be carried out at 0 degrees Celsius. It could be carried out at 50 degrees Celsius. So in order to show that this was carried out at 25 degrees Celsius and 101 kilopascals of pressure, we say that the standard enthalpy change is negative 890.3 kilojoules per mole. So this standard symbol right here means that the enthalpy change, because remember H is enthalpy, delta in chemistry means change, and then this is a standard symbol, so standard enthalpy change is going to be negative 890.3 kilojoules per mole, meaning that per every mole of methane that we burn, we release, because it's negative, 890.3 kilojoules of energy. That's how we read this, and the more you learn to read these numbers and symbols, the more enthalpy starts to make sense. So again, standard enthalpy change, standard symbol, H is enthalpy, delta is change, so let's write those down. I'll use blue here. Actually, the other is yellow. So the triangle means change. The H means enthalpy, which again is just heat energy. So change in enthalpy, changing heat energy, and then that means standard or at standard conditions. And when we read the numerical side, remember that negative means exothermic or releases energy. Otherwise known as exothermic, as we saw in the last section. 890.3 kilojoules means that's how much energy is released. Because kilojoules is what we measure energy in. And then this is per mole. Per mole of what? Well, in this case, methane, although that's going to change for every different standard enthalpy change that we see. But this is the basics of these symbols. And this is very important. So again, this is per mole, but in this case, it's per mole of methane that's being burned. Different enthalpy changes, which we'll discuss in this section, will have different per moles. So that's what everything means. Again, standard conditions meaning 101 kilopascals of pressure, 298 Kelvin of temperature, and everything is in normal physical state. And by everything, we mean the reactant. So we see that methane is a gas, which methane is normally a gas. Oxygen is a gas, which is normally what oxygen is in at room temperature and pressure. So that is the basic breakdown of what all the different symbols mean. So let's now go into the different types of enthalpy changes. Now, this is an important conversation. Why? There are 5 different types of enthalpy changes that we're going to discuss in the AS chemistry curriculum. There are actually more, and there's an extra one that we have already kind of brought up earlier that's not in your curriculum, but we will mention. But in reality, there's a lot of different standard enthalpy changes. The actual basics of this do not change, meaning when we look at the different enthalpy changes, and again, there are 5 in the curriculum for AS chemistry, they're all the same thing. They're all the amount of heat energy that is being exchanged, given off if it's exothermic or absorbed if it's endothermic. But when we look at the different standard enthalpy changes, what changes is the type of reaction they are for. So again, the actual base idea does not change. When we look at the standard enthalpy changes, we're simply looking at the amount of energy they're given off or absorbed by a process. What changes is what process is that. It's kind of like the idea of currency. If we have currency, for example, let's make a quick little chart here. So if we have currency and money, the idea of currency is the same regardless of what country it is. It is paper that we can exchange for goods and services, paper or coins or something along those lines, right? So currency is it's like enthalpy. Enthalpy is the amount of energy that is exchanged. Currency is the monetary thing that we exchange. When you go in different countries, you have different currencies. USA has dollars. Argentina has pesos. Japan has the yen. So on and so forth. Different countries have different currencies, but the idea of currency does not change. Currency is the same whether you're in the US, Argentina, or Japan. You are going to exchange currency for goods and services. That idea doesn't change. Enthalpy change is the same thing. Or enthalpy is the same thing. Enthalpy is just the amount of energy given off or absorbed. When we talk about the enthalpy change of formation, it's just for a formation reaction. It's the amount of energy given off or absorbed in a formation reaction. When we talk about the enthalpy change of neutralisation, it's just the amount of energy given off or absorbed by a neutralization reaction. When we talk about enthalpy change of vaporization, can't spell. It's about the amount of energy absorbed by the process of vaporization. Same concept, different applications. Again, with currency, same concept, different applications in different countries. So when we look at all of these different enthalpy changes, just keep in mind, we're always talking about energy given off or absorbed or energy exchanged. It's just going to apply to different concepts. We're first going to talk about the standard enthalpy change of vaporization, which is for a physical process. And then we're going to talk about the standard enthalpy of change of reaction, which is the most generic for any chemical reaction. Standard enthalpy change of formation, which is for the formation reaction of a specific compound. Standard enthalpy change of combustion, which is for a combustion reaction. And then standard enthalpy change of neutralization, which are for neutralization reaction. Each one of these is going to come with a very specific definition that I cannot stress enough you need to memorize. These are always going to come up in your test. At least one of these definitions will come up in your paper 2 or paper 1 exams, and it is the easiest point that you can get as long as you memorize the compound, or sorry, the definition. You need to memorize the definition, and it's the easiest point you will get. So let's start with enthalpy change of vaporization. And again, if we break down the title, this is very straightforward, right? Standard means standard conditions. We talked about this earlier. Standard means standard conditions. Enthalpy change means heat energy change. So we're talking about the heat energy change at standard conditions. That's always going to be the same for a standard enthalpy change. And then we have of vaporization, meaning during a vaporization process. Which, if we remember from like middle school, vaporization is when we convert a liquid to a gas. So the vaporization process of converting a liquid to a gas, the amount of heat energy change at standard conditions that goes along with this vaporization process, that's what standard enthalpy change of vaporization is. And we can see the symbol here. Again, the triangle is our standard symbol. I'm highlighting green like I did here. So that means, sorry, not standard. Our triangle means change. So it's in green, pink. So triangle means change. H means enthalpy. Our change or standard is the symbol. And then vaporization in the bottom is shown by a V. So this means standard, the symbol up here, enthalpy change, delta H, of vaporization, B. Now, we saw this in chapter 5. So this enthalpy change of vaporization, we actually discussed in chapter 5. The standard enthalpy change of vaporization is the enthalpy change when 1 mole of a liquid is converted into 1 mole of a gas under standard conditions. So there are a few parts to this definition. The first part to this definition is the enthalpy change when 1 mole, meaning the change in energy when 1 mole of something is, and then the second part, converted from the liquid into 1 mole of the gas. So, oops, and I went too far there. Liquid is converted into 1 mole of the gas. So 1 mole, very important for the standard enthalpy changes, of a liquid is converted to moles of a gas. So the process is liquid to gas. The amount is 1 mole of that liquid being converted to 1 mole of that gas. And then the third part to this definition is under standard conditions. Why? Because this is under a standard enthalpy change of vaporization, not just the enthalpy change of vaporization. So that green part, that standard, is shown in this part of the definition under standard conditions. The enthalpy change part is actually shown here, and I should probably change this color from blue to pink. So we have the enthalpy change, the change in energy, when 1 mole of a liquid is converted to 1 mole of a gas. So I'm going to change the blue to blue because this is the definition part. This is the vaporization part. So when 1 mole of a liquid is converted to 1 mole of a gas. Very important here, 1 mole. 1 mole. So the definitions are very specific. And these are the 3 things. If you have a definition question, it could be worth anywhere from 1 to 3 points for enthalpy change of vaporization. 1 point will mean that you get 1 point for everything. And then if it's just enthalpy change of vaporization and not standard enthalpy change of vaporization, you would not include the under standard conditions. So if this was a 2-point question, you will get a point for saying the standard enthalpy change when 1 mole of a liquid is compared to 1 mole of a gas, and then another point for the under standard conditions. And then if it was 3-point, you will get 1 point for saying the enthalpy change or heat energy change, 1 point for saying when 1 mole of a liquid is compared to 1 mole of a gas, that 1 mole would be bolded, meaning if it's not there, you wouldn't get the points. And then 1 more for saying under standard conditions, or 1 point, sorry. And again, that 1 point for under standard conditions is dependent on you being asked what is the definition of, or what do you understand by standard enthalpy change of vaporization. Each of these words is important. It's not good enough to have a close enough definition. A close enough definition might get you some points. If you want full points, or if you don't want to lose easy points on the exam, you will learn the actual definition because every part is important. Enthalpy change, that's what tells you it's a heat energy exchange. 1 mole of a liquid converted to 1 mole of a gas. The liquid to gas tells you what the process of vaporization is. The 1 mole of a liquid to 1 mole of a gas tells you what is that 1 mole of. Because we discussed how in enthalpy changes, the units are in kilojoules per mole, and that mole changes from enthalpy change to enthalpy change. That 1 mole in this case is moles of liquid. Oops. Moles of liquid are turned to moles of gas. And when we do mathematics later on, this is going to be very important. And then finally, the under standard conditions is important because it's standard enthalpy change and not just enthalpy change of vaporization. That standard means that you add these under standard conditions part to the definition. Because if this wasn't standard enthalpy change of vaporization, if it was just enthalpy change of vaporization, then that part of the definition, under standard conditions, would not be added. Now, unlike the other enthalpy changes, the standard enthalpy change of vaporization is a physical change, not a chemical one. This is a physical process, not a chemical process. So it's a physical change instead of a chemical change. Now, does that actually change a lot of our enthalpy change? Not really. It's still the same idea, the idea of that changing of heat energy, exchange of heat energy. It's just that for a physical process, it's a lot more logical whether the process will be endo or exothermic. If we're going from a liquid to a gas, in order to break the intermolecular forces, and you can start to have this conversation now as we pass more and more chapters. As we pass more and more chapters, we can have this conversation of putting everything together. Because water liquid needs to be compared to water gas, in this process, IMFs are being broken. Intermolecular forces are being broken. Oops. Particularly because we're looking at water here, hydrogen bonds are being broken to turn the water from liquid to gas. Because of that, because we need energy to break a bond or to break an intermolecular force, this process has to be endothermic. And that can be seen here because this enthalpy change is positive. Because enthalpy change is positive, we see that this is an endothermic process, which makes sense. So this is the equation that goes along with the standard enthalpy change of vaporization of water. Or another way to put that is delta HV standard of H2O. That's what this is the equation for. And this is very important because you will be asked to draw up equations that symbolize different enthalpy changes. Now, enthalpy change of vaporization, like we said, are always endothermic. And when we draw the equation, it's very simple. It's going to be, if this is the enthalpy change of vaporization of water, it's going to be water on the left, water on the right. If it's the enthalpy change of vaporization, let me use a different color here. If it's the enthalpy change of vaporization of X, so delta H standard V for X. And X could be any chemical. It doesn't really matter what chemical X is. There's just going to be X liquid, because we're doing vaporization, so we start with a liquid, yields X gas, because we're turning the liquid to gas. That's vaporization. This process is always going to be endothermic. So this is always going to be delta H is always going to be positive. And notice that we have no coefficients in front of X, or no coefficients in front of the water. Why not? Because the definition of enthalpy change of vaporization says, and going back to this, when 1 mole of a liquid is compared to 1 mole of a gas. So we always, when we drop these equations, need to pay attention to definitions because they're tied to the equation. We have 1 mole of H2O liquid turning into 1 mole of H2O gas. That's vaporization. So for every 1 mole of water liquid that turns into water gas, 43.9 kilojoules of energy are needed. That's why it's per mole of the liquid, of whatever we're turning into a gas. Now, like I said, if this was any other chemical, all we have to do is replace X for that chemical. So if this was delta H of vaporization standard of, let's say, ethanol, which is C2H6O, then all we'll have to do is say C2H6O liquid yields C2H6O gas. Because we're going from liquid to gas, it's 1 mole of each. All that changes is the chemical. They will never ask you what is this delta H, because there's no way of you just knowing that off the top of your head. But there are ways where we will calculate it, which we'll see in later sections. But this is something you will be asked to do very frequently, to draw up an equation for a specific enthalpy change. So for the case of vaporization, always liquid to gas of whatever chemical it is that we're looking at, always 1 mole. And you should know that this is always going to be positive because intermolecular forces, regardless of what they are, in this case hydrogen bonding for water, also hydrogen bonding for ethanol because it has an OH group, or whatever, if it was a methane, then London dispersion forces, whatever it is, we're always breaking bonds. So intermolecular forces are always going to be positive. So that's the enthalpy change of vaporization. Notice how it's a lot of theory and a lot of definitions, but not a lot of mathematics or any of that. That we'll look at later. But it's very important for you to learn these definitions very well and how those definitions coincide with equations that we are creating. And then in specific cases, certain enthalpy changes are going to have certain specific things you have to remember, like enthalpy change of vaporization always being endothermic because intermolecular forces are being broken. Or bonds if whatever we are boiling or vaporizing is ionic or metallic. So let's move on to the next enthalpy change. The next enthalpy change. The next enthalpy change is the enthalpy change of reaction. Now, out of the chemical reaction enthalpy changes, this is the most generic of them all. And again, we are going to break down this title. We're going to break down this heading, right? So again, standard means standard conditions. So those are going to be 298 Kelvin of temperature, 101 kilopascals of pressure, and everything is in the standard state, or the state at room temperature pressure normally is at. Enthalpy means heat energy. I'm mixing up the colors a little, but that's okay. And remember, heat energy is always calculated in either kilojoules or joules, although for enthalpy we use kilojoules. Change, which is pretty self-explanatory, is the change or exchange in energy. Meaning it can either be positive or negative. And then off reaction. This is a new part, right? Because everything else, a standard enthalpy change, that is in all of these definitions. Off reaction, meaning of a chemical reaction. So this one is a lot more generic. We're not looking at a specific physical change like we did with vaporization. We are looking at a specific chemical reaction. Now that could be any chemical reaction, but it's a chemical reaction in general. So again, R in the symbol, delta H standard R. R stands for reaction. Delta means change. The H means enthalpy, and the standard symbol is for the standard. So each part of the symbol means one part of the definition. Now, if we look at our definition, we'll see that enthalpy changes of reaction has also some key things that need to be added to the definition. So the first part is how these are all gonna start. The enthalpy change. Now, this always needs to be in your definitions. Either the enthalpy change or the heat energy change need to be part of your definitions. Why? That's what we're defining. We're defining the standard enthalpy change of reaction, right? So it is the enthalpy change. You can just say when an amount of reactant is shown in the stoichiometric equation reacts to given products. Because what of that? Not just the equation, but the energy change associated with the equation. So we're always going to start with the enthalpy change. Then we're going to move on to what of reaction means. When the amount of reactant shown in the stoichiometric equation react to give the products. What does that mean? That means that we're looking at the equation. When we say 1 mole per mole, we mean per mole of equation, if that makes any sense. Per cycle of equation. Per equation shown. So in this particular equation, we're going to look in here the reaction between hydrogen and oxygen to make water. So 2H2 gas plus O2 gas yields 2H2O liquid. So in this case, the per mole is per mole of oxygen in this particular one, because when we do one cycle of this, we use 1 mole of oxygen. So what this means, delta HR is equal to negative 572 kilojoules per mole, is for every 2 moles of hydrogen and 1 mole of oxygen that react, 2 moles of water are created. This is the energy that's released. So when we read the equation, the amount of reactant shown in the stoichiometric equation react to give the products. That means whatever is shown in this equation, that's how much reacts to give that enthalpy change. And then finally, we have under standard conditions. And again, the under standard conditions means because we have to have these under standard conditions because of that symbol. If we didn't have this symbol, if it was just enthalpy change of reaction, then we would not include that under standard conditions section. I should probably change that change to yellow here, just because that is part of a different color now. So when we look at this equation, how do we build this equation? Well, with standard enthalpy changes of reaction, the equation can or has to be given, or it has to be an equation that we can predict the products of and calculate the stoichiometric coefficients, meaning we need to be able to balance it. Because when we look at this reaction, what is this negative 572 kilojoules of? This means that 572 kilojoules of energy are released when 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water, liquid water. So that just means that this is the reaction, the equation that goes along with these 572 kilojoules. So if we did 4 moles of hydrogen and 2 moles of oxygen to make 4 moles of water, if we double this reaction, we will also double the enthalpy change. So if we reacted 4 moles of hydrogen, we will get twice as much heat being released. If we created 4 moles of water, we will get twice as much heat being released. If we reacted 3 moles of oxygen, we will get 3 times the amount of energy being released. So that's why these definitions are very important, because when we say the standard enthalpy change of reaction of the reaction between hydrogen and oxygen is negative 572 kilojoules, we mean that 572 kilojoules of energy are released, because it's negative, for every mole of oxygen that reacts with 2 moles of hydrogen to make 2 moles of water. We need the equation that is equivalent or that goes along with this enthalpy change in order for this to make sense. All right, let's look at the next one. Standard enthalpy change of formation. Now, this is a very important one because when we start doing the mathematics, we are going to use the standard enthalpy change of formation a lot. And again, we have standard, meaning standard conditions. We have the enthalpy, meaning heat energy. We have the change, which we don't need to define because it's just change. So standard conditions, heat energy change at standard conditions of formation. Now this is where it becomes very important. So formation meaning a formation reaction. Formation reactions are when elements in their elemental form are turned to compounds. So formation reactions are unique in that the formation reaction goes from elements in their elemental form to compounds. We're never going to have a compound as a reactant. We're going to have compounds as products. And again, we're going to look at this standard enthalpy change. So standard being the symbol up here, enthalpy being H, change being the delta or the triangle, and then the F being the formation. So the standard enthalpy changes of formation are, like I said, very often used in calculations for enthalpy changes, so they're very important. And it's very important for us to understand the definition. The definition for standard enthalpy change of formation is very specific, very unique. Again, we start with the basic, the enthalpy change, right? And that's, like I said, going to be in every definition. The enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. So again, 1 mole of a compound is formed from its elements. Very important here, this is 1 mole of a compound that is formed from its elements. Meaning that whenever we're looking at the enthalpy change of formation of something, when we look at the product's coefficient is always going to be 1. Because the definition for standard enthalpy change of formation ties down that product coefficient to be 1 mole. Because, again, this is not the enthalpy change when 3 moles of a compound are formed. It's the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions. And again, under standard conditions, we always add that when we have standard in the definition. So standard enthalpy change of formation definition, the enthalpy change, always going to be there. When 1 mole of a compound is formed from its elements, that is specific to formation under standard conditions. That is there because it's standard enthalpy change. If it was just enthalpy change of formation without the standard, then we will define it like this without the yellow section. So when we do a standard enthalpy change of formation, which can be either endothermic or exothermic, they could be either positive or negative. These do depend on the compound that you're making. We choose the most stable form of the elements as the reactants because the definition says when the compound is formed from its elements. So we're going to look at what elements is the compound we're working with made from, and what is the most common form of those elements, and then create 1 mole of the compound from those elements. So let's look at this. This is the enthalpy change of formation of water. So this is the enthalpy change standard of formation F of H2O liquid. And the state of matter does matter because this number would be different for gaseous water or for solid water. But this is the standard enthalpy change of formation of liquid water. So what does that number tell us? If the standard enthalpy change of formation of liquid water is negative 286 kilojoules per mole, that means per mole of water, in this case, formed, or per mole of compound formed, 286 kilojoules means that release, because negative, 286 kilojoules of energy. So for every 1 mole of water we create in this process, 286 kilojoules of energy are released by that process. Released again because it's negative. 286 kilojoules is the amount, and then per mole, in this case, because it's formation, it's per mole of compound, which in this case, that compound is water. So when we're creating these reactions, how do we do it? If I'm asked to make an equation for the standard enthalpy change of formation of liquid water, which is a very common question to be asked to create an equation for a standard enthalpy change of formation, I'm going to put 1 mole of the compound in the state that they're asking me for as a product. And then I'm going to look at what are the compound, or what the elements that compound is made of. In the case of water, water is made of hydrogen and oxygen. Well, what is the standard form of hydrogen? Hydrogen is part of Brinkelhoff, is part of the diatomic elements. And so when I put hydrogen, I'm not going to put H, I'm going to put H2. Because H2 is the most common form, or the most stable form of hydrogen. And that's going to be a gas, because hydrogen is a gas at room temperature. When I look at the O, oxygen, even though I only have one here in the compound, oxygen is also a diatomic element. It's part of Brinkelhoff. And so, because it's diatomic, I'm not going to put O here, I'm going to put O2. And again, oxygen is a gas at room temperature and pressure, so I'll put O2 gas. Finally, I have to look at my coefficients. Now, this is the part where you might get thrown off. Hydrogen is diatomic. We have 2 hydrogens on the product side, H2O. We have 2 hydrogens because it's diatomic. That one's easy, just a coefficient of 1. Because we need 2 hydrogens, 2 hydrogens. However, when we do the oxygen, there's only 1 oxygen on the product side. But when we have this O2, we have 2 oxygens on the reactant side. Now, normally what you would want to do is that you will want to change the coefficient on water. But with standard enthalpy changes of formation, we cannot do that. Remember, that standard enthalpy change of formation is locking, the definition is locking the coefficient for water, or for the compound being made, to 1. So we cannot change this right here. We cannot change this 1. So what do? In standard enthalpy changes of formation, it is actually fairly common to use fractions as coefficients. Because if we cannot make this 1 into a 2 to match the O2 in the left side, then what we're going to have to do is make this 2 into a 1. How do we multiply 2 into 1? We multiply by 1/2. And so we're going to have to put a 1/2 in front of this oxygen to make this 1 oxygen total to match both sides. So it's a very common practice with standard enthalpy changes of formation to put fractions as coefficients, because that 1 in front of the product cannot be touched. So again, what does this all mean? This 286 kilojoules per mole being the enthalpy change of formation of water. That means that 286 kilojoules of energy are released when 1 mole of liquid water is created from its elements in their standard forms. What are the elements in the standard form? 1 mole of H2 gas, because hydrogen is H2 when it's stable, and 1/2 a mole of O2 gas, because oxygen is O2 when it's stable. So this is going to require you to do something that you have learned naturally as you have gone through chemistry, but not super well, not something you've been paying attention to. Now you're going to have to consciously memorize these or learn these. And that is the most stable forms of most of the elements. Now that might sound daunting because it's 118 elements, but it's actually fairly simple and straightforward. Why is this simple and straightforward? Because even though there's 118 elements, most of them have the same standard form. There's only a few that you need to be worried about. So these are the standard forms of the elements. We have essentially 4 different groups that elements will fall under. The first group you learned about last year in honors chemistry, which are the diatomic molecules. The diatomic molecules are elements that will naturally pair up with themselves in nature, meaning that when they're found in nature, they're not just one atom of the element, but two atoms covalently bonded together. So, for example, the most common one being hydrogen. Hydrogen is H2 in nature, meaning it's a hydrogen atom bonded covalently to another hydrogen atom. Pretty easy and straightforward. Nitrogen is the other one, another one. So N2. N2 is two nitrogen atoms that are triple bonded together. Oxygen is O2, which is again double bonded oxygen atoms that are bonded together. So we don't find oxygen as O in nature, we found it as O2, this is the air that we breathe. F2, which is the fluorine atom, or the fluorine molecule, which is two atoms of fluorine covalently bonded together. And pardon those lines, those should be dots. So we have F2. And then all of the halogens actually do this the same way. Chlorine will be Cl2 with single bonded chlorine atoms. Bromine will be Br2, which will be single bonded bromine atoms. And then iodine will be I2, which are two iodine atoms single bonded together. So we need to remember that these 7 elements are going to be diatomic, meaning that when we write them in the reactant side of an enthalpy change of formation reaction, we do not write them as just F or just O or just N. We write them as diatomic, meaning H2, N2, O2, F2, and so on and so forth. And you should also remember the states of matter. Most of the diatomic elements are gases at room temperature, except for 2 of them. And they're both halogens. Bromine is liquid at room temperature, so Br2 is a liquid. And then iodine, I2, is a solid at room temperature. Other than that, they're all gases, all the other 7. An easy way to remember the diatomic gases is to remember Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine are the 7 diatomic elements. 1, 2, 3, 4, 5, 6, 7. Brinkelhoff. And if you remember that, then you'll remember what the 7 diatomic elements are going to be. Now, the next category of elements that we're going to have to remember, it's actually pretty simple. It's the noble gases. Noble gases are, like the name implies, always gases, so it's very simple to remember. They're always going to be G or gas for the state of matter. And because they don't react or bond with anything, noble gases are always going to be monoatomic, meaning that they're not bonded to themselves, they're just one atom. So we just write it as the symbol, so He gas, Ne gas, Ir gas. There is no subscript, because they don't bond with anything. So in nature, they're found as just the atoms in the gas state. Now I want to jump over the exceptions for a second and look at most elements. Now, most elements are very similar to the noble gases, only that they're solids instead of gases. For most elements, we're going to have solids at room temperature, and that's because most elements, 80% of the periodic table, are metals, are metal elements. Metals are always solid. And because they're metals, we just simply write them as their atoms, no the subscript. So they're not diatomic, they're all just metallic lattices, and we talked about that in past chapters. But they're just simply the element with a solid. So lithium, Li solid, titanium, Ti solid, aluminum, Al solid. So most elements, metals essentially, are just going to be the element's symbol with solid states of matter. Now, what are some notable exceptions? Some notable exceptions are going to be, there's some non-metals and metalloids, and one metal, which are a bit different or random. So, carbon be the first one. We talked about in chapter 4, I believe, or 5, that carbon has a lot of different allotropes. There's graphite, there's diamond, there are Buckminster fullerenes, there are nanotubes. But in most cases, or in the most stable conformations, carbon is going to be graphite. So you'll see it written as two ways. You will see it written as C graphite or simply C solid. I'm more of a C solid. So whenever we see carbon solid, it is understood that it is carbon graphite, because graphite is the most stable allotrope at room temperature and pressure of carbon. And think about it, that makes sense, right? We know diamonds require really high temperatures and really high pressures to be created. So that's the first notable exception. Carbon is usually C solid, but that solid does talk about graphite. The next one is the only metal on this list, which is mercury. Mercury, like most metals, is written as just the atom's symbol because it is monoatomic, or just, a metallic lattice. But mercury is the only one of the elements, or the metal elements, that is a liquid at room temperature. There are only 2 liquid elements in the periodic table. Mercury is the only metal, which is just Hg because it is a metallic element. And then bromine is the other one, which is diatomic and a non-metal. So one of each. Then the 2 that are probably going to be the most confusing to you are phosphorus and sulfur. Phosphorus and sulfur are tetraatomic and octaatomic respectively. So phosphorus is tetraatomic, it's usually P4, whereas sulfur is S8. So both of them solids at room temperature. Now, the main issue we see with sulfur and phosphorus is that even though phosphorus is tetraatomic and sulfur is octaatomic, in the Cambridge exam, we usually see them as just monoatomic elements in the solid state. So what you'll see in the Cambridge exam usually is P solid and S solid, not S8 and P4, which are the more common forms. Now, there are a lot of different forms of phosphorus and sulfur. There's red phosphorus, there's white phosphorus, etc., etc. But in order to simplify all of that on the Cambridge exam, what we'll often see is that they will simplify it to just P solid for phosphorus and S solid for sulfur. So understand that P4 and S8 are the actual forms, more stable forms of phosphorus and sulfur, but for the sake of the exam and simplification, they just use P solid and S solid. So those are the most common states, or the most stable forms of the states of matter. This is the general guidelines we're going to use for all the elements. Yeah, there are things on here that we haven't talked about, like the fact that silicon is usually a giant network structure, or a giant covalent network, but we still write it as just Si solid, so on and so forth. A few other metalloids that we're not going to talk about. But these are the most common elements on what we should remember. So, having said that, let's look at what this will mean when it comes to writing the enthalpy change of formation reactions. So let's say we're asked to draw the standard enthalpy change of formation of methane, CH4, solid. So again, this means the creation of CH4, of 1 mole of CH4, so when I leave this as 1, and that will be, actually this is not solid, I don't know what I'm talking about, that will be a gas. So let's take CH4 gas, that's going to be our product, because our product is always just 1 mole of the compound we're making. And then we got to look at what are our 2 elements that make up this compound. So we have carbon, we have hydrogen. So let's start with the carbon. We talked about how carbon is usually, the most stable form of carbon is carbon solid or carbon graphite. So we'll put carbon solid plus, and then the hydrogen, the most common form of hydrogen, because hydrogen is diatomic in Brenkelhoff, is H2, and hydrogen is a gas. Again, we need to remember the hydrogen is diatomic, and we need to remember the hydrogen is a gas. But these are things that you should have picked up along the way, and if you haven't, you will always remember the conversation we just had. Once we figure out what the elemental most stable forms are of these two elements, and we put them down, that's when we're going to do our coefficients. That's when we're going to do our balancing. In CH4, again, this has to be 1. So we have CH4. Carbon has to be 1, so we're going to leave that as 1. And then hydrogen, there are 4 hydrogens here. The form of hydrogen we have to use is H2 because it's the most stable form of hydrogen. So because we need 4 hydrogen total, we put a 2 in front of the hydrogen. So our equation is C solid plus 2H2 gas yields 1 CH4 gas. We could also be asked to do this for more complex compounds. So let's say we're asked to do this for the enthalpy change of formation standard for sucrose. Or let's do, glucose. Glucose is C6H12O6 and it's a solid at room temperature. So again, how do we start going about this? How do we start writing the equation for this? Well, again, we're going to look at the compound that we are doing the enthalpy change of formation for. That compound being glucose, C6H12O6. We're going to put just one of those with the appropriate state of matter. And again, this has to be 1, so this is not going to change. And then we're going to look at our 3 in this case, different elements. We have carbon, we have hydrogen, and we have oxygen. So let's start with the carbon. Like we said earlier, carbon, what is the most stable form of carbon? Either carbon graphite or carbon solid. Now there are 6 carbons in glucose, and because this does not change, this has to be 1 here, we can go element by element doing this because the elements are going to be separated in the reactants. So we have 6 carbons, so this has to be 6 Cs because we need 6 carbons. And then we're going to do plus. The next element is hydrogen. Again, what is the most stable form of hydrogen? Hydrogen is diatomic, so that's H2 gas in the gas state. And here there are 12 hydrogens, meaning on this side we need to match that, 12 hydrogens. And so in order to make 12 hydrogens out of H2, we need a 6 in front of it. And then plus, the last of our elements is oxygen. Oxygen is O6. Again, the most stable form of oxygen, the one we breathe every day, is O2 gas. That's the most stable form of oxygen, so that's what we have to put here. And then if this is O6, there's O2 here, so in order to make that 6, we need a 3 in front of it. So this is the enthalpy change of formation, the equation for the enthalpy change of formation of glucose. 6CS, 6 carbon solid, plus 6 H2 gas, because again, those are the most stable forms of the elements, plus 3 O2 gas yields 1, because this always has to be a 1, C6H12O6 solid. Again, why does this always have to be a 1? Because of the definition of enthalpy change of formation. The definition of enthalpy change of formation is the formation of 1 mole of that compound. Let's do one more. So let's say we're working with sulfur trioxide. If we want the enthalpy change standard enthalpy change of formation of SO3 gas, sulfur trioxide. Again, our product is going to be SO3 gas. And 1 mole of it because that is the definition of standard enthalpy change of formation. We're going to have 2 reactants. We're going to have the sulfur and we're going to have the oxygen. Now, when we do this, sulfur's most common form is S8. However, on the Cambridge exam, we're usually asked to do S solid. Not S8, they use S solid to simplify, so we can use S solid in our reactions. And there's 1 S in SO3, so we only put 1 S here. The issue comes when we do oxygen. Oxygen's most stable form is O2 gas, like we saw here. However, we are required here to do 3 oxygens. We have O2, meaning we cannot multiply that by a whole number to get 3. But we cannot change this coefficient. This coefficient has to be 1 because we're in enthalpy change of formation. So how do we get around that? Well, what do we multiply 2 to get 3? We multiply 2 times 3 over 2, or 3.5, because then the 2's cancel to get 3. So what is the enthalpy change of formation of SO3 equation? It's going to be S solid plus 3/2 O2 gas, because 3/2 times 2 is 3, yields SO3 gas. And this is how we create the equations for standard enthalpy changes of formation. So let's go back to our PowerPoint. So make sure that you remember these. These are some of these you'll have to memorize. Some of these, as you use them, you'll just remember if you don't know them already. The next enthalpy change is the enthalpy change of combustion, or the standard enthalpy change of combustion. Again, we have our usual suspects. This is a standard enthalpy change, meaning it happens under standard conditions. It is an enthalpy change, meaning enthalpy is heat energy. And it's heat energy change. I don't have to really put anything for the change, but a heat energy change. And then of combustion. This one should be pretty straightforward. Heat enthalpy change of combustion is for a combustion reaction. And if you remember from honors chemistry, a combustion reaction is when a chemical, which we'll call the fuel, reacts with oxygen, O2, to create usually carbon dioxide and water, although not all the time. But so we'll put here to create products. Those products, if this is a hydrocarbon, meaning carbon-hydrogen compound, will be carbon dioxide and water, but there are a few other things that we can make. So the symbol for enthalpy change of combustion, standard enthalpy change of combustion, is delta H standard C. C being the combustion, the delta or triangle being change, the enthalpy being H, and then standard being the standard symbol, that circle with a line. Now, this is often used for organic reactants, but can be used for elements combusting in oxygen to create things like sulfur dioxide and whatnot. What you will notice is that whenever we do this for an element, like sulfur reacting with O2 to create SO2, that's essentially the same as the standard enthalpy change of formation. So some of these enthalpy changes do have crossovers. The standard enthalpy change of combustion of sulfur solid is also the standard enthalpy change of formation of SO, in this case SO2 gas. Because notice, S plus O2 yields SO2 gas. 1 mole of a compound being made from the elements in their elemental form or standard forms. So we are creating the enthalpy change of formation, but it's also an enthalpy change of combustion. Why? Let's look at the definition. The standard enthalpy change of combustion is the standard enthalpy change, and again, that's going to be always there, enthalpy change, because that's what we're talking about in this whole section. The enthalpy change when 1 mole of a substance is burnt in excess oxygen. So the 1 mole for enthalpy changes of combustion are of what we call the fuel, or the substance being burnt. So 1 mole of a substance is burnt in excess oxygen. So again, we have that 1 mole of the substance being burnt. So in this case, the sulfur or the methane in this case are going to be limited to having that coefficient be 1 mole, and the coefficients of everything else will have to adapt to that. And again, of course, this is standard enthalpy change of combustion, meaning that this is under standard conditions, and that will always be there as long as our definition includes the word standard. Now, as you probably imagine, standard enthalpy changes of combustion are always going to be exothermic. When you burn something, it releases heat. That, if you ever burned wood in a fire, when you burn firewood on a bonfire, or whenever you burn propane when you're grilling, you notice that heat is being expelled by the reaction. So enthalpy change of combustion are always going to be exothermic. Now, the standard enthalpy change, like we said earlier, of combustion might be also the standard enthalpy change of formation of the oxide, meaning of a oxygen and element combination. So like we said here, sulfur being burned in oxygen to create SO2 can be the standard enthalpy change of combustion of sulfur, and it can also be the standard enthalpy change of formation of sulfur dioxide. Notice how the chemical changes. Why? Standard enthalpy change of formation is product specific, meaning we look at what the product being created is and it being made from its elements in an elemental form. But standard enthalpy change of combustion is reactant specific, meaning that we are looking at what is being burnt, a reactant. So even though these are the exact same thing, standard enthalpy change of formation of sulfur dioxide gas is the exact same number, the exact same thing as the standard enthalpy change of combustion of sulfur solid, we can call it two different things because the definitions have overlap on them. Now, most of the time though, standard enthalpy changes of combustion are used for organic compounds. For example, the burning of methane, CH4 gas. Burning of methane is a very common process for creating energy out of natural gas. So methane, CH4 gas, is burning, again, oxygen, 2O2, to create CO2 and H2O, and 2H2O in this case. So this is an example of when standard enthalpy change of combustion is used for an organic compound. Now, we will talk about organic compounds in chapters 14 through 18, but this is what we know as a hydrocarbon. And that should be pretty simple to see because the word hydrocarbon comes from hydro, meaning hydrogen, and carbon being carbon. So hydrocarbon is simply a compound made out of carbon and hydrogen. CH4 being made of carbon and hydrogen is hydrocarbon. So this hydrocarbon CH4 is burning oxygen, and when hydrocarbons are burned, they always create the same two things: carbon dioxide and water. We talked about this in honors chemistry when you learn how to predict the products of combustion reactions, that whenever something's made out of hydrogen and carbon, or even a little bit of oxygen, it's always going to create carbon dioxide and water. Now, the enthalpy change of combustion of methane means that we're burning 1 mole of methane in excess oxygen, and the enthalpy change of combustion there is going to be negative 890.3 kilojoules per mole. Again, this is always going to be negative because enthalpy changes of combustion are always negative. So this is heat expelled or given off. So heat given off, and that means that we give off 890.3 kilojoules for every mole or per mole of, in this case, methane, CH4 gas being given off. All right, so keep that in mind. That's what the enthalpy change of combustion is. Now let's move on to the last of the enthalpy changes that we are asked to learn in this curriculum for AICE chemistry. The last enthalpy change that we're going to be asked to learn is called the standard enthalpy change of neutralisation. Now, before we get into that enthalpy change, let's review really quickly what a neutralization reaction is, or what we called last year an acid-base reaction. An acid-base reaction is a reaction between an acid and a base, an acid being classified as a compound that releases hydrogen ions in a solution. So acids are very common, right? They're something that we've been studying since we started studying chemistry. And most acids will have the formula HNX, where H is hydrogen, N is the number of hydrogens that are in the compound, and X is an anion that tells us how many hydrogens there are by its charge. So for example, HCl is an acid, H2SO4 is an acid, HNO3, HC2H3O2. If we look at these, the reason why they have different number of hydrogens is the charge. So let's take HNO3 and H2SO4 for example. H2SO4 is H2SO4. This 2 comes from the fact that the sulfate ion is SO4 2-. Because hydrogen ions are H+, for every S2- charge on the SO4, we need 2 hydrogens to cancel them out. On the other hand, in HNO3, there's only 1 hydrogen because the nitrate ion, NO3, is -1. So there's only 1 hydrogen needed with its +1 charge to neutralize the nitrate. So just keeping this in mind, you might have different numbers of hydrogens in an acid because of the charges of the anion. But you always have hydrogen. Because acids release hydrogen ions in solution, they always have that hydrogen they can give up. An alkali, on the other hand, or what we usually call a base, is a water-soluble base that is going to release hydroxide ions in solution. Now, bases can come in a lot of different shapes and sizes and a lot of different types of bases. And we will talk about them as we go through the curriculum. But the most common, the easiest to understand type of base is the alkali. They're water-soluble compounds that give off hydroxide ions, OH- ions in solution, which essentially means all you need to have a base or an alkali, water-soluble base, is a hydroxide compound that dissolves in water. Because of the solubility rules, we learned that group 1 hydroxides, as well as heavy group 2 hydroxides, heavy meaning Ca and down, Ca and lower, so calcium, strontium, barium, so on and so forth. So heavy group 2 hydroxides are going to be alkalis or water-soluble bases. So group 1 and heavy group 2 hydroxides. NaOH, KOH, SrOH2. Why OH2? Because again, this is a group 2 element, so it is 2 plus in charge, whereas hydroxide is -1. Barium hydroxide, BaOH2. These are all alkalis. They're all water-soluble bases. So, what is an acid-base reaction, or otherwise known as a neutralization reaction? It's simply just a reaction between an acid and a base. In that reaction, the reaction between an acid and an alkali is going to yield in the creation of water and a salt or ionic compound. Remember, a salt, whenever we say salt in chemistry, does not mean sodium chloride necessarily. Salt means ionic compound. So a neutralization reaction is always going to lead to two products, water and an ionic compound or salt. Well, let's take it into the most common, the one that is you will see all the time, the reaction between sodium hydroxide and hydrochloric acid. The hydroxide from the base will react with the hydrogen from the acid, and together they will always make water. What the product is going to be, the product is just simply going to be the combination of the cation from the base, in this case because sodium hydroxide, the sodium, and the anion from the acid, which in this case, because we're using hydrochloric acid, is chlorine. So we get that Cl and that sodium coming together and making the compound sodium chloride. Of course, you do need to take into account the charges. Chlorine and sodium are both +1 and -1, so when they combine a 1-to-1 ratio. If this was magnesium instead of sodium, or actually strontium instead of sodium, this will be SrCl2, because we will need 2 chlorines for every 1 + 2 strontium. But again, the point here is that when an acid and an alkali react, they're going to create water and sodium chloride. Always, the ionic equation for this is simply going to be the hydroxide ion and the hydrogen ion combining to create water. So the hydroxide from the base is going to react or combine with the hydrogen ions from the acid, and together they will make water. That's always the ionic compound, because this salt is always going to be aqueous, meaning that the cation from the alkali and the anion from the acid are always going to be spectator ions, creating that ionic compound or salt, but that ionic compound or salt is always going to be aqueous, making a spectator ions. So this is a bit of review from earlier chapters, but it just always helps to start tying things together. So this is what we call neutralization reaction. Reaction between an alkali and an acid. So it stands to reason then that when we talk about the standard enthalpy change of neutralization, we're simply talking about the standard enthalpy change for a neutralization reaction. So again, we have the usual culprits here. We have Standard, meaning under standard conditions. We have enthalpy, meaning the heat energy. And again, enthalpy change, meaning heat energy change. So heat energy change under standard conditions of neutralisation. Of neutralisation, meaning of a neutralisation reaction, meaning the reaction between an acid and an alkali to form water and a salt. So when we look at a symbol, delta H standard neut, the neut means neutralization. We're going to use N because it's used for a different enthalpy change. Standard symbol means standard conditions. Oops, that should be green. Delta meaning change, and H meaning enthalpy. So standard enthalpy change of neutralization. Now the standard enthalpy change of neutralization deals with a very specific reaction, which is that acid-base reaction or acid-alkali reaction we talked about. And so the definition is very specific. Again, it's the enthalpy change because that is always going to be there in every enthalpy change definition. Enthalpy meaning heat energy, change meaning the change in heat energy. And then we get when 1 mole of water, so the constant in neutralization reactions, the thing that never changes is the fact that we always get water as a product. So the one coefficient here is stuck to water. So 1 mole of water being in the definition means that the water that's created is always going to be 1 mole. So the enthalpy change when 1 mole of water is formed by a reaction of an acid with an alkali. And again, because this is standard, it's under standard conditions. So this is the specific part here. 1 mole of water, so we get that 1 being stuck to the water, is formed by the reaction of an acid with an alkali. So we're always going to have an acid and an alkali as the reactants. Again, we'll stick with the same reaction, sodium hydroxide and HCl. And then that is always going to create water and a salt or ionic compound. So H2O being water always being there as a product, that is what the 1 mole, the per mole in the enthalpy change is always tied to. So we're going to write this reaction up as the reaction between the alkali and the acid with water being 1 mole. So standard enthalpy change neutralization are usually exothermic because when acids react with bases, those reactions usually release energy. And we can see that. So the standard enthalpy change of neutralization here for the reaction between sodium hydroxide and hydrochloric acid to create 1 mole of water and 1 mole of sodium chloride is negative 57.1. Again, negative meaning energy is released. So 57.1 kilojoules of energy are released when 1 mole of liquid water is created from the neutralization reactions between sodium hydroxide and hydrochloric acid. That H2O always has to be 1. So if we change this, so let's say we talk about the reaction between, this is between strontium hydroxide SrOH2, aqueous, and HCl. Again, in this reaction, we need to make sure that when we put here the product, this product, water, H2O liquid, has to be 1. So we need to build everything around that. Plus, in this case, because it's strontium and chlorine, strontium is a Sr2 plus ion, chlorine is Cl minus. When we make that compound, it's going to be SrCl2 aqueous. So like I said, this has to be 1, which means 1 HCl, or sorry, 2 HCl, no, 1 HCl needs to react with SrOH2, but we only need 1 OH, because remember, 1 OH minus plus 1 H plus makes 1 H2O. So because this H2O has to be 1, we need 1 hydrogen, and only 1 hydroxide. We have 2 here. So how do we fix that? This is going to be 1/2 OH2. Because half times 1 OH2 means we get the 2's cancel, we have 1 hydroxide. It makes 1 water. But that half SR means that we need to reflect the half SR here, meaning this is 1/2 SrCl2. And now it makes sense. 1/2 SrCl2 means we have 1 chlorine, which is only 1 chlorine here, 1 or half SR here, and then the 1 hydrogen with the now 1 hydroxide, because OH2 times 1/2 is just OH, makes a 1 water. So we gotta always remember to make that water 1 H2O. That is what defines the standard enthalpy change of neutralization. That's the last of the enthalpy changes that are in your curriculum. Now, that should be followed up by the fact that that does not mean you will not be asked about enthalpy changes that you will have to figure out. Mainly those of other physical changes. Because we talked about the enthalpy change of vaporization. But what about other enthalpy changes that are physical? For example, we understand from our earlier conversation that the enthalpy change of vaporization of a compound standard is, let's say compound X, and we'll just use placeholders like X, is whenever 1 mole of X goes from the liquid to the gas state. And that's because this is for vaporization. And vaporization is when we go from liquid to gas. What about the enthalpy change of fusion of X? Now, what is fusion? Fusion is just fancy chemistry term for melting. So what about the standard enthalpy change of fusion of X? Fusion means melting. Well, the process of melting is going from a solid to a liquid. So nothing changes. The only thing that changes is states of matter. We still have 1 mole of whatever is melting turns into 1 mole of whatever is the liquid is. 1 mole of solid to 1 mole of liquid. If we are talking about the standard enthalpy change of, let's say, sublimation. Remember, sublimation, delta H sub, in this case, standard of X. Again, this is not something you learn, but if you know that sublimation is the process of going from solid to gas, then it should be very straightforward to say, okay, the standard enthalpy change of sublimation is X going from a solid 1 mole of X, because it's always 1 mole, to X mole, 1 mole of X as a gas, because that's what sublimation is. So just know that you, even though you were not directly asked or learned what delta H of fusion and delta H of sublimation is, you could be asked about them on any other change of state of matter, because all it is 1 mole of the first state turns into 1 mole of the second, depending on what the state of matter changes are. You should know what sublimation is. You should know what melting is, or fusion, that you might have learned right now, because you learn about them in science classes all throughout your career in middle school and high school. Don't get lost in the fact that you've never heard about them, because part of the chemistry curriculum and Cambridge curriculum is critical thinking. Just focus on the fact that you know what the state of matter changes. If it's sublimation and it's from solid to gas, then you put solid to gas, whatever that compound is. So if it was carbon dioxide, delta H of sublimation, standard of CO2, then that would just be CO2 solid turning into CO2 gas, and the energy change associated with that process. And again, it's 1 mole to 1 mole, because whenever we would deal with physical changes, it's going to be a 1 mole to 1 mole. This is true of a lot of different physical changes, enthalpy changes. So just keep in mind, don't get caught up in the fact that you didn't learn it. Learn to think critically. Learn to use your brains, because especially starting with this chapter, there's going to be a lot of critical thinking involved, if there hasn't been already, which there has been, right? So just keep this in mind, that you might be asked about enthalpy changes that you were not directly taught, but if you know what the process is, then it's just the enthalpy change related to that process. And that is it for chapter 6, section 2. I will see y'all in the next video.